Just put some 20 people in here, that would be nice. Can you check YouTube? Okay, you don't have the link. Okay, I will start. Yeah. Okay, so I'm going to start now. So I welcome one and all for this edition of the Wednesday Colloquium. We have a very special guest, Professor Tony Donne, all the way from EUROFuion, who's going to talk about progress along the path towards fusion electricity. So, but before Professor Donne really starts this colloquium, I would like to sort of tell everyone who is listening via YouTube or for the first time through Zoom, the NSF Wednesday Colloquium is actually part of a rich tradition of TIFR's method of science sort of dissemination. It was started by our founding director, Professor Homi Bhabha, who thought that it would be a nice idea to get all the natural sciences faculty get into under one auditorium, one roof for 1 hour on every Wednesday and listen to lectures from leading experts from around the world who would at that time, when at the start of TIFR, would actually visit physically the TIFR Institute and Infrastructure and Facilities. And this would allow for sort of the scientists in TIFR to interact not only with the expert, but also while listening through these talks, interact with each other and start very nice collaborative, sort of discussions across physics, chemistry, and biology. So today's lecture is no different. It's very important, in fact, for our energy needs. And we have Professor Tony Donne, who is going to sort of elaborate on a recent breakthrough in generation of fusion electricity. I would now like to request Professor Shishir Deshpande from Indian Plasma Research and ITER India's main person to formally sort of introduce Professor Donne for this colloquium. Over to you, Shishir.
Thank you, Jyotishman. This is a pleasure to introduce Tony to this very important event, which is TIFR's traditional colloquium. And good afternoon to all the remote participants, colleagues at TIFR and IPR. Dr. Tony did his PhD in 1985 and has had almost 4 decades of very illustrious career in nuclear physics as well as fusion. And in 2010, he's been working at Eindhoven University of Technology, where he was heading the diagnostics and heating systems, 2 very crucial systems for the plasma. And later, from 2014, he's been coordinating as a program manager for the EUROFuion as a CEO, for coordinating amongst the 28 member countries, the directed fusion research amongst all the labs. And in 2020 onwards, he is now chairing the International Tokamak Physics Activity Committee, which coordinates with the whole world in directing their respective fusion research towards specific targets and especially to address ITER's scientific needs. So actually, I mean, we couldn't have found anyone better for today's talk because he's going to give us a perspective on not just JET, but how eventually Europe looks forward to bringing fusion to the grid. So I extend my own words of warm welcome to Tony and hand over the meeting to Tony.
Thank you very much, Shishir, also Arun. It's really a pleasure for me to contribute to this colloquium. I deeply regret that I couldn't make it to Mumbai this time of the year, so maybe in the future. But still, I think it's very nice opportunity to interact with you on the European Fusion Program and certainly also in JAD. So the way I need to see how my slides they were working before. Okay. So the contents is I will show you a little bit about what Eurofusion is. Then say a few words on the European Fusion Roadmap, and I will then show you highlights of what we call the Horizon 2020 program. That's the name of a 7-year framework program in Europe, which started in 2014 until 2020. And we are now in Horizon Europe, so we just started with, let's say, the coming 7 years. So I will also give you a look into the future. So let's start with the overview. Eurofusion is, well, basically all these countries together, 28 countries, 25 of them, the blue ones, they are European member states. Switzerland and the UK, they are associated. The UK was part of Euratom, but since Brexit, they're now kind of separate. We are also very happy that Ukraine is part of Eurofusion, but of course we know about the problems, and I think I gave the European flag color to Ukraine to also because of the present problems there. So totally we have 30 research institutes. Germany has 3, but all the other countries have 1. And behind them there's 152 university groups to be exact. And we involve roughly 100 MSc and 700 PhD students. And roughly 4,000 people are working for Eurofusion, with Eurofusion. Not all full-time, but at least 4,000 people are involved. What Eurofusion has brought to Europe is the joint operation of all the tokamaks. So before we started in 2014, JET was the only device which was 100% used by the European community. All the other machines, they were national devices. And of course, what you get is each device has its own agenda. All the labs, they want to focus on those topics which give you FISREF letters and nature papers. But there's also gaps. No one wants to do disruption studies or something like that because it could be harmful. And we are now doing a much more horizontal programming. We set the priorities of our research and then we choose the best machine. So in this way, overlaps are, well, still there because sometimes they're needed to do size scalings, but also you get rid of the gap. So at the moment, 5 of these machines are operational. So JET, Astex Upgrade is actually here in my garden. TCV in Switzerland, MAST also in England and West in France. Coming online next year is Complex Upgrade. It's a copper coil high field tokamak. GT60 is a device we are working on together with Japan as part of the broader approach, should come in operation later this year. And DTT is a device which should come in operation in 5-6 years from now in Italy. It's also a superconducting tokamak. Additionally, we united the stellarator community on a single device, Wendelstein 7X, which is in Greifswald in northern Germany. So all the people doing stellarator work are going there for experiments. And similarly, we also try to have joint operation of all the linear devices and can see they are spread all over Europe. And even in Ukraine, we have one device in Kharkiv. The device is still there. The plasma physics laboratory is still undamaged, but many parts of the institutes have been heavily bombarded. So we don't know what this means for the future of the device. And then additionally, we have also, of course, theory and modeling. And as a backbone for that, we have 5 advanced computing hubs. These are groups of computer scientists, mathematicians, people in artificial intelligence, etc., which are helping the fusion scientists to port their codes on our high-performance computer, which is in Bologna in Italy. It's a 10 petaflop computer. And so we usually have once a year call for CPU time at this device. Let me now go to the roadmap. Our roadmap doesn't have really times because it's event driven. The final goal of the roadmap is to lay the science and technical foundation of the fusion power plant. And by far the most important device is ITER. And well, I don't have a time scale. At the moment, the first ITER plasma is foreseen at the end of 25, and full performance is thought to start at 2035. These are still the official dates. There might be some changes coming and announced soon, but these are still the official ones. What you see, ITER will not lead you to the fusion power plant. ITER will not generate electricity. For that, we need another device called DEMO. At this moment, we're working on the conceptual design. And the idea is that the concept design should be finished 5 years after first plasma in ITER, and construction could start 5 years after ITER reaches full performance. At the moment, this would be around 2040. And then around I think at the moment, 2054, 2055, we would have first electricity production. And to guide the ITER research plan and to help also the demo design, we're doing presently research on all the devices which I have shown on the previous slide. But that's not all. Demo will really, let's say the materials in demo will be exposed to enormous neutron bombardments. Typically, materials near the plasma side of the machine, they will encounter typically 50 to 100 dPa. dPa, for those who don't know, is displacements per atom. So any atom in the surface of these materials will be displaced 50 to 100 times during its lifetime, which means we need to develop materials which are robust, and we need to test them. We do that in materials test facilities, which at the moment still are largely fission reactors, but in the future also dedicated neutron sources. I will say a few words more about it. Stellarator, we're working on that. We see that as a long-term backup solution. Stellarator has some advantages above a tokamak. There's no disruptions. There's some instabilities, edge localized modes, which are very nasty, are not there. It's a continuous device, but technically it's a little bit more complicated. And of course, what is very important, to get fusion on the grid, it should be affordable. So we need to work on concept improvements and innovations which help to lower the cost. I often get the question, can you already work on demo while ITER is not yet working? So here you can see the ITER operational plan from 25 till 2040. And this is the demo phase where we're now in the conceptual design phase. And you can see that each time in the ITER phase, information from ITER is flowing into conceptual design. Ultimately, so in the beginning, it's information about the magnets, the vacuum vessel, the assembly, and in later phases, it's, for instance, the operation of the tritium breathing blankets and the long pulse QS10 operation. So we still have possibilities to adapt the design until a certain moment. So let's now go to the highlights. And I start with the highlights from the JET campaign. I added this additional slide to really pay tribute to the people who have been doing the work. I'm just a messenger. As I said, well, I'm leading this organization in which 4,000 people are involved. So I'm not really directly involved in the science myself, but we have a team of task force leaders which are coordinating. And in these experiments, about 300 people were involved. A very important decision we took in the order of, I think even 15, 16 years ago, is this graph from Jürgen Roth, which was published in 2009. And this would show the accumulated amount of tritium in ether, where the safety limit is 700 grams if you use different raw materials. And you can see that if ether would have a carbon wall, as at that time all the tokamaks had carbon walls, this would mean that ether could have in the order of 100, 150 discharges. And then you need to open ether to get the tritium out, because tritium binds to carbon, and carbon also forms dust. So a lot of the carbon is lying as dust on your machine. So then already it was stated that if you have a beryllium wall with a tungsten diverter, you're much better off, and you only need to get the tritium out after maybe 5,000 discharges, 10,000, which is once every so many years. So we decided to have a major rebuild of JET. The decision was taken in 2004, but then with all the preparation and all the work, the actual work was done in 2009, 2010. And you can see we did that completely with remote handling. So there were no people going into JET. We did it with robotics. And we changed the inside of JET to beryllium, and the diverter was changed to tungsten. And the idea was to perform a program which looks like that. So we have now what we call the ether-like wall. Although honestly, I think ether should call their wall the JET-like wall, since we were first, but okay, that's just a small detail. But let's call it the ether-like wall. So important is to develop the plasma scenarios, because operating a device with a metal wall is not easy. It's like, well, recently I had many talks with journalists, and one asked me how difficult is it? And then I came up with a comparison. It's like you're basically getting your driver's license in an automatic car. And then immediately when you get your license, they put you in a Formula One car, and they ask you to drive around with 300 kilometers an hour. Of course, it's difficult. You need a lot of training to work again with the machine. So this really took a lot of time. We needed to confirm indeed that the tritium retention is reduced. And of course, the ultimate proof of the pudding was to do the DT experiment. So good news is that indeed the fuel trapped in the wall is reduced by more than a factor of 10. I think it's even closer to a factor of 20. So here you can see the fuel retention in atoms per second in 10 to the 19th atoms, with a carbon wall and with, let's say, the beryllium wall with tungsten diverters. So this is really good news for ether. Then we started operations. So the first operation, we really had problems to meet the old carbon data, so which are the gray points. And up to 2014, we just got to this level, and then we got a saturation. And the problem was that tungsten was coming in the machine, and we needed to find recipes to keep the tungsten out, which meant that we needed to seed gas in the edge, so usually neon and argon. We had to apply central heating also to flush the tungsten out. But then gradually we got back to the performance. So these are data which we did until, I would say, early 2020. And we were more or less back to the old performance. So that's the moment when we said, okay, now we are ready to do DT experiments. In the meantime, we not only knew how to operate the machine better, but we also, since the previous DT experiments, which were in 1997, 25 years ago, we improved quite many of the diagnostics. We had more channels, we have more accurate measurements, better spatial resolution, better temporal resolution. At the same time, also our theories and models have been improved. And this really made it possible to look into much more detailed in the physics. And some of the key results, which I take you through, is the influence of the fuel mass on plasma properties, also novel heating methods to heat DT plasmas, alpha particles, validation of ether predictions, and also the energy production. As said, we have been doing experiments largely for many years only with deuterium plasmas or sometimes with hydrogen. But this was again the first time that we were using tritium. We have 60 grams of tritium on site. And typically in each of the jet plasmas, we only need fractions of a gram to fuel the plasma. So here you can see already a positive effect. We are looking here into the threshold to get into the high confinement mode. So for the non-fusion people, the high confinement mode is a mode in which you have a better confinement of the plasma. Already the term is self-explaining. But you need a certain threshold energy to get into. And what we noted is that going from deuterium to a 50 deuterium tritium mix, the threshold comes down. Actually, for pure tritium plasma, it's even a little lower, but it's really like a reduction of almost 30%, which is good news for ITER. Then we did experiments going from pure deuterium plasmas to pure tritium plasmas. And we saw that this has a pronounced effect on especially the profiles in the ferry pedestal. So here, and this also shows how good our diagnostics are. This is just like 20 centimeters of jet plasmas. And these are measurements with our high resolution Thomson scattering system. So you can see that the isotope we're working with has not too much effect on the temperature, but it has a pronounced effect on the density. So when we increase the tritium content, the density at the edge goes up. And these were really pieces of information we didn't have from the previous campaign. Of course, the tritium is 3 times as heavy as the hydrogen, basically 1.5 times as heavy as the deuterium. So you can expect that the erosion from the wall is also somewhat higher if tritium impacts on the wall. What we noted, it is indeed the case, but still the increase in erosion is well within the tolerance for ITER. So I think we're perfectly fine there. Then what we explore is a novel heating method, because we have this beryllium wall. There's always a little bit of beryllium impurities in the plasma. And we explored that now for ICRH minority heating. So basically part of the heating was done with this novel type of heating, which is also, let's say, a technique ITER can use, because ITER has the beryllium, where you actually heat preferentially the beryllium, and the beryllium then collides with all the plasma particles and increases the energy. Alpha particles were created not in, let's say, very large amounts, but sufficient to see the interaction of the alpha particles with the plasma. And here you can see a graph where you can see this high-pitched ringing of the plasma due to the alpha particles, which is as predicted by our theoretical models. And then what was also very important is we have been developing models, and in principle, the model calculations were done before we did the DT campaign. So you can see the spread of the different models we have. And these are the data we put now on top. And you can see that our data are now exactly following the models, which is good news, because the same models predicted ITER will get 500 megawatt at 50 megawatt input power. Now, what did we achieve? So in 1997, we had, the world record fusion energy was 22 megajoule. So typically 4.5 megajoule for like 5 seconds. And we had this very short blip where we reached 16 megawatt instantaneously, but very short. In this campaign, we decided to focus on the 5-second discharges. The 5 seconds is the limitation of JAD. If we operate at high performance, since we're using copper coils, no superconducting coils, after 5 seconds, we need to stop, otherwise the coils overheat. But we then got here the first results. This is with a 50-50 deuterium tritium mixture. We have 42 megajoule for, let's say, roughly 5 seconds. And we also did measurements in a more tritium-rich plasma, where we ultimately achieved now our new world record of 59 megajoule. But this is completely in line with all our theories. So that's really good news. And here you see a picture. We also have a movie. I don't think this is, no, this is just a still picture. So apart from that, we now at least can to journalists that we have a very recent work record. I always felt sorry if you need to say that, well, the best results in fusion ever was in 1997. Of course, we made a lot of progress during this time. So I really think that the JET-DT experiments have brought fusion energy closer. We are preparing new scientists and engineers, but it was very important also to train people to work with tritium because the last experiments 25 years ago, the people which were involved there, they are slowly retiring and leaving fusion. So we needed really new people. We could test, let's say, DT fusion in ether-like conditions with an ether-like wall, very important. We have in these 5-second discharges much more information about the plasma, and we have a list now of 60 different topics which we're going to work out to papers. We're expecting a special issue of nuclear fusion in the course of 2023. We validated the models which extrapolate to ether and also other devices beyond JET. And of course, the world record is a nice extra, but for us, the science was more important. I switch now from JET to another other work we're doing to give you a feeling that we're not only doing JET, but I take you immediately to another world record. And this is a world record achieved in Magnum PSI in the Netherlands. Where we mimicked 1 full power year of ether in just 18.5 hours. So Magnum PSI is a linear plasma simulator. We have 1.5 to 10 to the 25th particles per square meter per second on a target. And since the machine has a superconducting magnet, it's really continuous. And here you can see ether-grade materials for the diverter tested before the test and after. And you can see that after the test, all the materials survive. Only when we apply a helium plasma, the material gets blackened, but there's no cracks. It's all, let's say, very nice. We're doing work on the various tokamaks, a relatively new child in the family is a master upgrade, which came in operation last year. And a special feature of master, apart from it being a spherical tokamak, is the Super X diverter, where you spread the footprint of the diverter over a much larger surface. And what we have seen is that the reduction of the diverter heat flux is by a factor of 10. And we need also a lower density to reach detachment, where you detach the plasma from the actual wall. So again, very good news. What we don't know yet is whether this is demo compatible, because you really need coils very close to the plasma, but it's a nice feature. In the same area, we are working on upgrading a number of devices. So TCV in Switzerland will be equipped or has been equipped with these baffles and extra coils to have more flexibility in the snowflake configuration. Astex is being equipped with an upper diverter to make double null discharges. We are working on the actively cooled diverter in West. So this is really an ether type diverter, and also the linear devices are upgraded. In the stellarators, well, the good news is Wendelstein came in operation in December 2015, and it really had the best performance for stellarator ever. And we're very happy with the results. And this year, the device will come back in operation after a 2-year shutdown for upgrading. I will say a few words more. In the materials area, we have been working on tungsten. Tungsten is a very brittle material. Hey, this doesn't work with... how can I get this movie started? I need my mouse there, one or the other way. That's strange. Okay. Cannot get the movie. Let's wait. No. I can turn off my laser pointer, then it should work. You see, tungsten is very brittle. It breaks immediately. And this is a new way of tungsten manufacturing, which basically has resulted in a very ductile tungsten, which doesn't break. which is very good, of course. What we are testing now is how radiation sensitive this material is. So I think it's a very nice way forward. In the materials, we are also working on the design of IFMIF donors. The idea is that construction of this device should start in the course of this year in Spain. So we hope for a construction decision. And together with Japan, as part of the broader approach, we're testing the prototype accelerator, the LIPAC, where we have a deuterium beam which is accelerated to 20 MeV. And at the moment, this is already the world's most powerful deuterium beam. IFMIF will have ultimately a 40 MeV beam at 10 megawatts, where we hit a free-flowing lithium target, which then gives a neutron spectrum, which is reminiscent of that in a fusion reactor. In the area of demo, we finished the conceptual design of, the pre-conceptual design of demo. And actually this month, a special issue should come out of the journal Fusion Engineering and Design, which collects about 30 papers, which together give the status of this design. At the end of 2020, we had a gate review where we had an external panel which really looked in detail to the design and to say what is important for our demo system. Here you can see a kind of artist graph of how demo could look like.
Oh.
For those of you,
Yeah, okay.
I hear some noise in the
Future
background.
plant. EUROFuion.
Can you mute your microphone?
Demo.
Sorry, wait a second. I'll just check.
Yeah. Okay. Thank you.
Yeah, here. Please go ahead.
Okay. Thank you. So you can see that for people working on ITER, well, it looks similar. We have an assembly hall, we have a tokamak hall, we have magnet power building, we have heating buildings, diagnostics buildings. Of course, the difference is a turbine building, the cooling towers, because we will generate with this device 500 megawatt electric. Important, this is also, let's say, part of safety, which we're doing for demo, but it's basically working with the materials coming from JAD. They are intermediate level waste because it's all tritiated. We now develop techniques to lead the materials through kind of bubblers, where there's some isotope. You can see that the activity before and after the bubbler, we get reductions by 2 to 3 orders of magnitude, and the detritiation factor is, let's say, well above 99%. So very good. We're looking in breathing blankets. This is a complicated slide, but just to give you a flavor, in the breathing blanket, we are flowing a liquid metal, typically lithium lead. But it's in a strong magnetic field, so we need to look at the hydrodynamics of this fluid. We're doing studies there, so this is really theoretical work. At the same time, we're working on coatings because we want to protect the breeder material from the rather corrosive lithium lead. And we found that aluminum oxide is very good because it has a permeation reduction factor of more than a factor of 1,000. So also good progress in this. This is work we're doing on high heat flux testing in Gladys, which is actually here across the street in Garching, where you can see also materials exposed up to 20 megawatt per square meter for 500 cycles. And so these are ITER-like tiles, but also tiles where we changed, for instance, the cooling pipe or the connection between the cooling pipe and the tungsten. And we even did a test up to 32 megawatt per square meter. We're working on diamonds for microwave windows. So this is one of the largest windows I know of, 18 centimeters diameter, 2 millimeters thick, which typically can be used as booster window for electron cyclotron heating or for microwave diagnostics. So just a few recommendations which came out of the gate review. What was very important is that they said, well, it should not be research which drives the design of a machine, but it should be the design which drives the research. Otherwise, you never get a machine. And I'm worried that I see in some countries, I was last week participating in this White House, well, not participating, following the White House summit, where I see that it's very much the research which then says what the reactor should do. And then in the end, the research is always coming with new ideas. You never get to your reactor. We need a central team, which we are now setting up. We need, well, the most critical areas are the plasma scenario. Very important is to find a plasma which radiates the energy as uniformly as possible to the blanket. We don't have that scenario yet, and so we need to work on that. Critical areas are further the breathing blankets and also the maintenance, remote maintenance of the blanket diverter. We need to work on concepts where you really can have fast maintenance, because in a fusion reactor, if you want to replace a blanket module or you want to replace a diverter cassette, you want to do it typically on a Monday morning and not in the first half year of year 2062 or something like that. And of course, the building is also important. Cost consciousness is important. For instance, one of the breathing blankets we were working on, only the breathing material would cost €2 billion. And that's very expensive. So we really look also there for cheaper solution. Important is to also think about the industrial supply chain, not only develop materials in the laboratory, but have a good connection with industry to make sure that they can manufacture what you design. We need to develop a knowledge management strategy. For instance, now we have many people in ITER which know how to build ITER, how to make the buildings, how to make the magnets. But of course, we need to keep these people then back and get its knowledge into demo. Licensing, very important. We again see the discussion around the ITER licensing at this very moment. And ultimately, we need to train the new generation of scientists. So then I have a number of slides on the program we just started. So the main objectives are to construct and commission ITER. I should say in all transparency that this is not something EUROFuion is doing. We are not building. We have ITER and the domestic agencies doing that. But we are much more involved in the second, securing the success of ITER operation via preparation experiments on present devices, as the experiments on JET, which I've shown. We developed the conceptual plan of demo. We are doing that in Europe. We have some role in the design of the neutron source. So our role was mainly the engineering design and the safety reports, but the ultimate construction will be again Fusion for Energy, the European Domestic Agency, and the Spanish consortium. We want to advance the stellarator to see whether that has any possibility as a possible fusion power plant, training our new generation of scientists, engineers, operators, and of course important is also the industrial competitiveness. Now, if I take you year by year through this phase, again, well, the results of JET were already the success of the first year. We're 1 year in the program. It's maybe nice to mention that 59 megajoule was generated by only 170 microgram of fuel. And if you compare that with fossil fuels, you would need in the order of kilograms. What was also a nice achievement is that on 19th of January, we did the 100,000th jet pulse. And of course, on 9th February, we had the new world record. But this year, Wendelstein will come back in operation. So after the last campaign, we had a shutdown, which is almost 2 years, 2.5 years. Because we wanted to equip Wendellstein with an actively cooled diverter. And this means the machine is now ready for operation up to 30 minutes and at high power. We hope to have the construction decision if Donne. And finally, also GT60 in Japan is expected to come in operation in the fall of this year, typically October, November. Next year, Compass Upgrade will come in operation. It will be a copper coil device, but it will be cooled copper, nitrogen cooled copper. in order to generate 5 Tesla on axis. Additionally, we will have a full-fledged facility review. So we really want to look at all our facilities and decide which are really now the most important ones. GT60 will start its full physics campaign in 2024. So then we will have 6 months of operation. And well, of course, ITER still has its first operation, as they announced on the 23rd of December 2025. But I think everyone knows that will be later, but we are waiting for the official announcement. DTT will come then maybe even a little bit before ITER. It's a superconducting device, a little smaller than GT60, but it specifically focused on testing advanced diverters. And the aim for the conceptual design is to finish that in 27. Apart from all this science, we are coordinating all the education in Europe. We are supporting about 700 PhD students, which are scattered over all the laboratories. We are supporting 100 plus MSc students at universities. And additionally, we have a grant program for postdoc researchers and for engineers. And the engineering program is really focused on areas where we really have needs. We are supporting MSc students via FuseNet, which is the Fusion Education Network. And then maybe also important is that we are doing technology transfer, because we are developing a lot of technologies in laboratories. And ultimately, we also want industry to profit. And a very nice success story was a company which worked basically with us, or actually with our predecessor organization, EFTA, in the development of superconducting cables for ITER. And this company, Bruker, now is a leader in the world market for medical resonance imaging. And they have an annual turnover of 1 billion. This is an example. I was myself involved in the Netherlands. We wanted to get Dutch industries involved in ITER. And there was this company which was forming metal plates in a certain shape with explosives, because that has the advantage that you don't develop cracks, and you can also get structures which are more extreme. And so I went to this company and asked, can you do this trick with 6 centimeters thick stainless steel plate? Because my question was, can you make the vacuum vessel of ITER? And they did a test of a 6 centimeter thick plate, 2 by 2 meters, which they could blow with TNT in, let's say, a shape which was within 0.1 millimeter accurate. We took this company to a number of industrial exhibits, and they are now making the cockpit of the Airbus A380 with explosive techniques. So you could say that the Airbus is now using fusion technologies. Other examples are palladium membranes, which we use for the tritium in work with tritium and jet, which are now used in chemical, automobile, remote handling. We started with jet, but it's now used for, well, for instance, the laboratory which developed this is involved in decommissioning the Fukushima plant, for instance. But the robots are also used for space science and medical surgery, etc., etc. So this brings me more and more to my last slide. We have performed quite well over the last 7 years. It was the first time in Europe that we started working with a fusion roadmap. Before that, all the labs were just doing what they thought was important. But this has helped to coordinate the fusion research, to avoid too many overlaps, and also put focus on some gap areas. The pre-conceptual design was completed, which I think was a very good success. It was a very holistic design. And of course, the other more recent success is the DT2 campaign at JET with the World Record Fusion Energy. We have an ambitious plan for Horizon Europe, which is again fully aligned with the roadmap, which has many challenges, where we also look forward to collaborating with, let's say, all the partners in the world. So we are collaborating with most of the ITER partners. We are very happy for that, because I think together we can beat this challenge of getting to fusion electricity. I have actually, as a kind of backup slides, also more in detail what we are going to plan, but I don't think I take you through now. But I can send, probably I need to send a PDF file of my presentation to Shishir and Arun, which then can be distributed to all the participants. So you can really at your leisure look at, let's say, all the information there. So I think I stop here to leave also time for questions. But thank you very much.
Can you hear the applause here in the auditorium?
Wonderful
Yeah.
talk.
Yeah, thank you, Tom.
We have 117 participants and some connected collectively from different rooms. And so it's open to now question answer session.
Yeah. So
Maybe I can ask.
yes, yes. So there's a question in the lecture theater.
Can it be heard?
Yeah, you can.
Okay,
I
so
can hear it. I think I can hear it.
okay, thank you. So it's a very nice and very ambitious project which it look like. So I have a question. Like it's a big project which is happening. I mean, it's a global project, mostly covering Europe. So how it is funded? For example, like you have something in Japan and also in Europe, some other countries. So like the things that is being developed in Japan, it's completely funded by Japan, or like how the funding is really
How is the funding
divided?
done?
Yeah.
Or
Managed-
centralized, yeah,
managed or
managed.
something. So
Yeah, the funding of the activities in Japan, so the ones which connect to the broader approach. So the broader approach was a kind of setup which was invented when we had to decide where ITER is going to build, either in Rokasho in Japan or in Europe. And then ultimately, Europe offered that if Japan would agree with the site of ITER in Europe, that Europe would invest also in some of the activities in Japan, which include GT60. It includes the IFME-VEDA, so this linear particle accelerator, and also the IFERC, which is the high performance computer they used to have. And this basically is financed. So the European finance comes via Fusion for Energy, not via EUROFuion. And typically, Europe has contributed 300 million euro to GT60. So GT60 is 50% funded by Japan, 50% by Europe. Now we are going into the expectation phase. EUROFuion is chipping in because Fusion for Energy, they know how to convert money into steel and stainless steel and concrete, but they are not experienced in exploiting devices. That's our experience. So we are now taking over. So we are funding European scientists to go to Japan to join the experiments. We're funding engineers to work with let's say, with the IFME-VEDA. EUROFuion itself is funded by means of a grant. So we are not a legal entity. So the 30 national research laboratories, they got their act together. We developed a roadmap, and we then put forward a proposal to the European Commission. And the European Commission has given us money. So for now, the first 5 years, we got 550 million from the European Commission, which we can distribute. So we set the priorities and we distribute it. But the laboratories, the national laboratories, need to match that with another 50%. So basically the 550 million, which we give out, is matched with another 550. So in total, our budget is like 1.1 billion. So which is kind of sizable. I still hope that we get more money because the budget in the present framework program is like 30% less than in the previous, which is especially related to the UK being no longer associated, and that's another 200 million euro. So we are still talking and hope they will associate, because then let's say we'll get an additional budget. I should say for fairness though that the UK now joins our program with their own budget. So in principle, they are matching with 100% of the resources since they don't get money from us.
Okay.
I hope this answers.
Thank you.
Thank you. Thank you, Tony. There's another question?
Yeah. So I just wanted to know what was the thing that made this record? What series of developments, or what actually there's any particular development that triggered this 59 megajoule leap? To the lay scientist, not somebody who is well versed in tokamaks.
Oh, well, we always said we are not going to advertise that we want to make a world record. For us, what was very important is that if we go back to that slide, I don't know where it can go, but for us, very important is to have this 5-second discharge. Well, there was also important is the length, because the typical energy confinement time is in the order of half a second to 1 second in jet. So the energy confinement time for the non-fusion people is the typical time the plasma cools off. So it's kind of factor which says how well your magnetic isolation is. And anything you can do over this 1 second is already kind of sustainable. So the plasma is already in a kind of steady state. Of course, 5 seconds is still short, but it's long enough to study all the processes in the plasma and to make some statements. Whereas if you go for a very short blip, and we could do that, we could focus and try to beat the 16 megawatt record, which seems to be, let's say, more important than, let's say, this. But I think in the end, if we want to have fusion energy, the stationarity of the process is more interesting, because this really gave us now the option to look into the interaction of the alpha particles. And with such a short discharge, it becomes much more difficult. So we really decided to go to the 5 seconds. And then the 59 megajoule really came from, and then I need to go back more to the tritium, sorry. I think it's a few more slides. To this slide, where you can see that the fusion power scaled very strongly with the input power. And at the moment at JET, we were limited. We had bad luck in a sense that our ether-like ICOH antenna developed a virtual water leak, and we had to couple that off. So that means we had 4 megawatt less. And also one of our PINIs, the neutral, so we have 16 neutral beam injector modules, and one of them also was not functioning. So we had only 15. So and that's at basically the maximum power which we got. So we could get in the order of, let's say, 10 to 11 megawatts on average then during 5 seconds. So ultimately we got the 59.
Thank you.
Okay. Thank you. Thank you, Tony. There are 2 questions from the Zoom audience. One is by Professor Alak Ray. Alak, please unmute yourself.
Yeah. Very informative talk. I have 2 questions. You mentioned somewhere in the beginning that if you line the internal surface with beryllium rather than carbon, there are certain advantages. How much, for the particular type of reactors that you had been doing this, or you have this in mind, how much beryllium would be needed, and where would this beryllium be sourced from?
Yeah, exactly.
And can I ask a second question immediately? Because
Yes.
I do not have
Yes.
the opportunity later. ITER and many other fusion power experiments are very largely international collaborations. And in particular, one of the nations in the ITER collaboration has had a particularly brutal and invasive war launched against Ukraine. So how do you expect this collaboration to politically and manage itself properly in the future?
Okay, thank you for these very, very good and well, actually also nice and important questions. I think with the amount of beryllium, well, the beryllium in jet is beryllium on a N-canal backing. So the actual layer of beryllium is like very thin. It's millimeters, so that the total amount of beryllium is not that very high. In ether, it's kind of similar, and I don't know exactly where the beryllium comes from. I know that Kazakhstan, for instance, is one of the countries which has quite some rich beryllium mining, but there might be also other countries where.
Sorry, I didn't get the name. Which country?
Kazakhstan.
Kazakhstan.
Yeah, so I don't know how many kilograms. I should say that in an ultimate fusion reactor, the wall will be very thin. And because the neutrons need to pass the wall and lose their energy in the blanket rather than in the wall. So we don't need very much material on the wall. So so in demo, the actual wall loads will be much lower than in ether. So in ether, you still can have a relatively thick wall. Then on the collaboration with Russia, I think there's two elements. One, I cannot answer for ether because ether is indeed a collaboration in which Russia is a very important partner. And I don't know yet how Russia will react. Of course, as fusion, we are also working with Russia. We have a number of contracts. We are doing a number of irradiations at the moment because they have a reactor with a very high neutron flux. But immediately after the beginning of the war, we suspended all the contracts. And we also closed the account of Russian researchers on our high performance computer. So we are really rather strict. These are European guidelines. What is less clear, and next week I have a board meeting where we need to have a conclusion. We work with many also Russian scientists which involve in our work. And well, there's many scientists, they are also opposing, let's say, the war, but unfortunately not publicly, because I think in Russia, as soon as you say something in that direction, you're arrested. What I find, and I sometimes say this anecdote, when I think Shishir was probably around when I made that announcement in the ITPA a number of years ago that Ukraine had joined EUROFuion. And then a person from the Russian delegation stood up and he congratulated me by this fact because he said, well, since the Soviet Union fell apart, we cannot work with the people in the Ukraine. And now they are basically joining EUROFuion. We can work again with them via EUROFuion. I found that very heartwarming, but it's very difficult. And we now see also some of the European countries, they have their own sanctions. And some they even don't allow their people to have publications with co-authors from Russian institutes. So it's not about the co-author, but they don't want to have the Russian affiliation. So we need to see how we solve that. Because you cannot, let's say, hold up all the publications until this war is over and maybe the sanctions are taken away. So we are discussing that. So I cannot say yet a final decision on this. I hope this answers your 2 points.
Sandeep.
Okay. Yeah. Now, next question by Professor Sandeep Trivedi. Sandeep,
okay.
Could you ask your questions? Yeah.
Thank you. Thank you very much. Thanks a lot for a very wonderful talk. I'm sorry, I'm completely out of the field, so I apologize if my question is naive. Also, I missed somehow your first few transparencies. But my question is this, going from your very impressive results at JET to say ITER, at least as far as stationarity of the plasma is concerned, do you feel now that you are more or less assured about being able to achieve that at least for ITER, or are there big question marks there? And more generally, if I can ask, what are the key scientific challenges you feel vis-a-vis the ITER project? Thank you.
Yeah, well, a very good question. Sorry for not having an introduction on what fusion is in the beginning of my talk. Well, the prediction, actually, this slide, which you see now, shows that ITER will be able to, well, this slide doesn't show, but the models which we developed here and which we validated, the same models show now that ITER will achieve its 500 megawatt at 15 megawatt input. So that's good. On the length of the pulse, of course, in JET, we are really limited by the copper coils and the 5 seconds, but there are various superconducting devices working already in the world. Like, for instance, East in China. There's also K-Star in Korea, and very soon GT60 in Japan, which are working already with plasma discharges which go up to 1000 seconds. And this is also what ITER is going to do. Of course, they're still working on a somewhat lower performance than we are doing here in JET, but this is a very good technology. So what ITER should do, it should connect the high performance, where we learned a lot from JET, with the long pulse operation, where especially the machines in Asia are contributing. Of course, in Asia and in India, you have yourself also SST1, which hopefully also will contribute soon to this challenge. Now, on the main challenges for ITER, I see the main challenge for ITER is to put all the pieces together and to put the assembly together. I think scientifically, I'm convinced ITER will work, but it's a rather big complication. At one moment, one of the critical issues at ITER is the fact that the first 2 vacuum vessels, which were delivered by Korea, they are not exactly what they should be in shape. And now the nuclear regulator, for instance, is questioning whether the welding of these 2 sectors could be done in a safe way. So ITER needs to demonstrate that. And there's all kind of things like that. So I would say putting the assembly, once ITER is put together, I'm convinced ITER will work. The challenges for the machines after ITER is to find plasmas which don't have, let's say, instabilities at the very edge, which are really stationary, and which also highly radiate. So of the fusion power, most of the power needs to be lost by radiation from the plasma. And you want to do that as uniformly as possible and from the edge of the plasma, not from the center. And we are slowly getting there, but there's still a lot of development work being done in that area. So I hope this answers your question.
Thank you. Thank you very much.
Thank you. Thank you, Sandeep. I'll go to Dr. R. Ganesh, and then there are 2 chat questions that we'll take. Yes.
Hi, this is Ganesh. I'm from Institute for Plasma Research. Thank you for a wonderful talk, Tony. There is this new development about plasma which have a negative triangularity, and there is a lot of talk about at much low energy or input power, the confinement times are going to be much better. So do you have a comment or what you foresee for ITER operation vis-a-vis this new configuration, I think, which TCV and other machines are exploring? That's one question. If I'm allowed, I'd like to ask a related question.
Yes, Dr. Ganesh. Yes, please.
Yeah, this is not technical. This is more about like Europe has a handshake with Japan with a broader approach. If you have to make a handshake with India, for example, what would you come up with as a couple of main inputs? Thank you.
Okay, very good questions. Again, I want to start to answer. I forgot your first point. What was it again? Sorry. Getting older. Can you shortly repeat the first point?
Yeah, the first point is nowadays you have something called negative triangularity.
Oh, yeah, I got it. Sorry, I got it. Yes, sorry. I just slipped out of my. Yeah, negative triangularity is very important. We are testing it to some extent in the present devices. So Astex and TCV, we're doing some experiments. TCV is let's say very nicely equipped for that. Where do I have it? Because TCV has this very nice kind of rectangular vacuum chamber. So they can make all kinds of plasma. It was also there that the negative triangularity was explored first. We did it at Astex. We are in, let's say, the design of Compass Upgrade and DTT. We also have, let's say, looked specifically at negative triangularity to allow this kind of operation in a more optimized way in these devices. Because the point with all devices like Astex, but also ITER, is that they have the positive triangularity shape. And if you go for negative triangularity plasma, it's naturally a much smaller plasma. And so we're doing experiments. I don't think that ITER will do much in negative triangularity. I think ITER will really steam full power towards getting us to QS5 and QS10 operation with positive triangularity plasmas. I'm not sure whether they can make negative triangularity plasmas, but certainly there's a program ongoing to look at the merits of negative triangularity and whether in the future we should base ourselves much more on these kind of machines. Now the second point is, gosh, I'm really getting.
So the handshake between Europe and Japan versus yeah.
Very important. Sorry for this. So the handshake, I think what would be, let's say, very important. I cannot say, let's say bluntly, a number of topics. We had a kind of intensive collaboration with India on JET, and for some time we have been considering to have ELM perturbation coils, so RMPs in JET, where India was doing some tests. But at some point we didn't get the financing, and this collaboration stopped. I would say what is important for any collaboration is that we put our plans together. So in principle, I can send you the roadmap, the implementation plan. And you need to look what is in India important, what are the topics which for India really matter, and then see are there any topics where we can have mutual benefit. We're doing something similar with China right now, where China is very aggressive in their approach. We have some discussions where we can try to find, let's say, collaborations of mutual benefit. And I think for any collaboration, that's important that we, let's say, not for every individual element in the collaboration, but overall, there should be a kind of balance. And I'm sure we can also find these topics with India. But important is then to maybe set up a workshop where we discuss what are the Indian priorities, what are the European priorities, and see are there any topics where we then can, let's say, focus on.
Okay.
Thank you very much.
Thank you, Dr. Ganesh. Now we move on to the chat questions. There are 3 chat questions, Tony. First by Dr. J.B. Singh. Can beryllium alloys be used for the lining, as coating beryllium must be very challenging?
Well, it depends what kind of alloy you have. So if you have beryllium alloys with some other heavy elements in, then you again get the problem with, let's say, that you have the advantage of beryllium is still a relatively light element, and it's fairly benign if beryllium comes into your machine. If you, let's say, go to an alloy, it depends very much on what are the elements in the alloy. So I'm not sure whether we ever looked into that. For the, I think for JAD, it worked quite well with the beryllium coating on the Inconel tiles.
Okay, thank you. The next question is by CBP. I'm not sure the name of the name. What would be the auxiliary power requirement for a fusion reactor as a percentage of usable output power, say for a 500 megawatt power station?
That's also a very good question. The idea is that our demo, which we are designing for 500 megawatt electric, and that has a reason. So 500 megawatt electric is in Europe an amount of energy where you can dump the energy on the grid. You don't have to consult the grid operator. If you would go to 1 gigawatt electric, then you have each time you make a tokamak pulse, you need to talk, basically call the grid operator and say, hey, we are making a pulse, can we do it or not? So in that sense, it makes you more flexible, and still it's a value which is high enough to show that you are really able to generate electric power. The thermal power of this plant should be in the order of 2,000 megawatts, so a 2 gigawatt thermal plant. And the typical input power would be, I think, typically in the order of several hundred megawatts. So, but of course, we are accustomed to talking about the power which is fed into the plasma. So when I talk about, let's say at JAT, we had Q is 0.33, which means the heating power, the 59 megajoule, was 3 times as much as the heating power we put in. But this is not, let's say, taking into account the electricity which it needs, because then JAT would be much less. For demo, the 500 megawatt electric is really net electric power which we produce. So there's really electricity coming out of it.
Okay, so there's a next question from Maya. Recently, there is a lot of interest in spherical tokamak research technology development in Europe and worldwide. Do you see this would influence the demo power reactor design significantly within the EU demo timescales? Also, there are several private players coming up in fusion startup. How do you see its influence in for the fusion program in general?
Indeed, again, very important questions. We are, well, in our demo work, we are focusing very much on, let's say, ITER. We think demo would be very good if it's based on extrapolation from ITER. And one of the reasons is the nuclear licensing, because ITER will go through a lot of nuclear licensing. And if you use similar technology, it saves you a lot of time in getting the licenses. So that's one thing. The other factor which we have seen in our modeling is if you try to go to a more compact tokamak, like the spherical tokamak, basically you are able to have a much higher power density, especially if you go to high temperature superconductors, like CFS in the United States and Tokamak Energy in the UK are doing. They're saying that they will have typically 20, 23 Tesla on the coil and maybe 10 Tesla on the magnetic axis. Means you have a very tiny high power density plasma, but it also means that you have a relatively small plasma wall. So you still get quite big neutron load on the plasma wall. And in principle, in these compact devices, the neutron loads to the wall are higher than that in the more larger classical demo. And I never hear the teams talking about that. So I think it's good that the private companies are working on this. Out of the box thinking is good. It's good to see that investors are putting in money. I must say that they also, usually these companies come with a very aggressive timescale. They all promise fusion in 3 to 10 years from now. And I noted that this time scale is basically the maximum time scale an investor finds interesting. So if I would go to an investor and say, hey, we're working demo, it's the best idea in the world, and we're going to generate fusion in 2050 and 30 years from now, then this person says, well, sorry, I'm not interested. This is too long. So they really want to see a potential profit in 10 years. And this is why these companies often work with 10 years. And what you often see also for some of these companies, which are already around for 25 years, like Tri-Alpha, TIE, has been established in 97, General Fusion in 2002, Tokamak Energy in 2008. They already at that time, they said we have fusion in 5 to 10 years, and it's still the same. So each time they report on a so-called breakthrough, and they, well, really a little progress is sold as a tornado in a glass of water. And yeah, so I think they need to work with it 10 years to attract investors. So I'm personally not, let's say, really of the opinion that they will be much faster than we are with the demo approach. But it's good. I think it's good. And maybe if one of these companies is successful, I'm very happy because, you know, fusion is good for everyone. And the first who makes it work, I think, is in a good position, but it's good for the world as well.
Okay. Thank you. Thank you, Maya and Tony. Okay, Sanjay is asking on the chat, nitrogen-cooled normal conducting magnets seem very good option. Can we get more insight into this 5 Tesla magnet?
Yeah, I don't have personally the details because the compass upgrade is a Czech device. So it's completely operated by Czech Republic. As EUROFuion, we are going to fund in a liquid metal diverter in this device. But we're not involved in the magnets, but I can give you the contact details if you like, the person who is responsible for the machine, and they can give you the details of the magnets.
Okay. Thank you. Thank you. The last question from Polomi Chakraborty in BARC. Is there any ongoing project on liquid metal interaction / corrosion under the EUROFuion umbrella?
Yeah, so we're doing at the moment a number of experiments in different devices where we testing especially the Kepler porous structures, which could be, let's say, used for the future diverter. And we are also looking into corrosion. And so we're looking into the different well, also different materials, so lithium, but also tin and gallium arsenide. Gallium arsenide, gallium. But yeah, we're looking into that, and of course in the corrosion aspect as well. Okay,
Shishir has a question. Shishir, could you unmute? Yes.
Yeah, Tony, I once again thank you for a absolutely wonderful broad exposure, although rich technical. I'm sure it contained everything, technology, science. I want to ask you a question about vision. What structure exists in Europe which maintains continuity of vision over a long period of time? Because these demo, ITER, etc. are long duration projects and people will come and go. So what is a organizational stabilizing structure that you have which maintains this against, you know, vagaries of different people coming in and going out?
Yeah, there's two things. One is the roadmap is really a document which has vision until the fusion power plant. So our roadmap really covers the period until typically 2055 or something like that. Of course, the roadmap is more detailed for this short-term period, and then a little bit less detailed for medium-term, and then long-term is somewhat more vague because what you're going to do here depends also on the outcomes of the research here, which you don't know. So at least this gives a long-term vision. We had the original roadmap was developed in 2012, and here is the link to the roadmap, or you can also use the QR code. And in 2018, we needed to update it because when we were starting in 2012, ITER was still promising first operation in 2019. And I expect that, well, typically every 6-7 years, you need to look at the roadmap and revisit. So that gives already the long-term view. The other is, and let me see, that must be somewhere around here. A little bit back, sorry. I skipped, I'm now lost, I think. I think it was
what I'm hinting
what we're doing is, sorry, this slide. We're working on no, it's not there, sorry. We're working on a knowledge management strategy. So at the one hand, we are going to do a human resource survey actually in the course of this year. We did the last one in 2015 to see what are the competences which we have presently in the field, in all the laboratories, but also in, let's say, ITER and fusion for energy. We try to also consider what kind of competences are needed in the near future, because we then have to go back, for instance, to the bachelor programs and the PhD programs to train the engineers with the proper skills. At the same time, we are working now together with ITER and Fusion for Energy on a knowledge management retention strategy or knowledge retention strategy, so that people which are well, finalizing their work at ITER, which could be because, for instance, the magnet are finished and the people become, well, basically unemployed, to use these people then in the design of the demo magnets. And lately, we have hired quite a number of people which have been working in ITER, which retire now from ITER. And we pay them still like for 2 years contracts, so they come to Garching to work with our young engineers in order to transfer their knowledge to the young people. But it's a very important element which is often forgotten, especially because it's such a long-term project. And so the knowledge management, knowledge retention is absolutely important. And this is the only way to really talk with all the organizations and see what are the competencies now, what do we need in the future, and how do we prevent losing competencies?
Right, I understand that, and these are very important points, but how do we interface, or how do you interface with the government or European Parliament, which allows it a stability to continue the program year after year? That is, very important.
Well, I think in Europe we are kind of lucky because our fusion program is each time decided for 7 years. So our budget is in that sense very stable. So although our budget is now lower than I had hoped for, but it's now stable for 5 years, and I know already the budget I will get in 26 and 27. Yeah. Although officially it needs to be assigned to me. So for 7 years, I have this stability. In the course of 25, 26, my successor, because at that time I will be retired myself, will have the task to write a proposal for the next framework program. And what helps is that in most of our meetings, we have people from the European Commission sitting as observers. So we continuously have contact with them. And this helps also to prepare the European Commission that they can take the proper decisions at the proper time.
You have a regular briefing with the Commission and the European Parliament.
Yes, well, with the European Commission, I would say I have almost daily contact with the people which are responsible for fusion there. And I have, well, let's say, every 2-3 weeks I have a meeting. So daily contact means I need to phone someone to. With the parliament, it's slightly less frequent. But for instance, I gave a similar talk as this one to the Atomic Questions Working Group, which are all the representatives from the 28 different countries which are preparing for the Council of Ministers meeting. So in that sense, it gives direct contact with the members of parliament. And we regularly also organize events or meetings with the members of parliament to keep them informed. And this is very important.
Thank you, Tony, so much.
Thank you. Thank you, Professor Shishir. So I would like to then, if there are there any other questions in the Zoom?
No.
No, okay. And in the audience here in the auditorium? No, I don't think so. So Shishir, are there any questions from your end or any?
No, I don't see any hands.
Okay. Okay. So thank you, Tony, for this wonderful colloquium, very insightful, and really had a breadth from science to the political connections and the budget of such, cross-border collaboration. So thank you very much for joining and giving us your time. I also thank Professor Shishir Deshpande for getting this connection done with Tony and allowing TIFR to host this very important session. Also, I want to thank Sandeep and Professor G. Ravindra Kumar for sort of putting this together for the TIFR audience here. And with that, we come to the end of this colloquium. I want to thank 115 odd people who had joined in by the Zoom session for tuning in, as well as would like to tell you that the series continues next week with one of our TIFR's own ex-faculty giving a talk. Professor Mohit Randeria is going to come back and give a talk in condensed matter physics and some of the work that he's been doing from Ohio State University. So please join us next week at 4 p.m. For another session of the Wednesday Colloquium. And with that, I would like to conclude the session. And thank you so much.
Thank you very much.
Tony. Thank you, TIFR.
Yeah. Bye-bye.
Bye.
Bye.
I think